Okay, so this is an extra tutorial on addition and looking at column methods of addition mainly, but when we've got more than two numbers and we want to use traditional bookkeeping accounting techniques without the use of a calculator. So let's start with a string of numbers. We've got, let's say, 64, just choosing any number here, but sticking to two fingers, so we'll have 23, 39 and 42. So when we're adding these, we've said before that we don't necessarily need to go into column methods, and when we don't want to use a column method, we can simply pair up the numbers like this, and that halves the problem. Obviously, if we had 5 numbers here, we would just add that on at the end. But we've got 64 add 23 gives us 87. And here we've got a slightly more difficult sum of two numbers. We've got 39 add 42, but if we add one to one side, take one off the other side, it makes life easier. So we've got 40 and 41 gives us 81. We can then add those together. We should put our equal sign in here. So 87 add 81 gives us 168. So pretty straightforward, but obviously there are places here where we could have made mistakes, and if we had a longer string of numbers, it would get much more complicated. So what's the column addition method? Well, if we write down the numbers in columns very carefully, because we don't want to, we want everything to be aligned vertically so that we don't confuse ones with tens, for example, we end up with something like this. And what we're going to do is work right to left. Now, when we're looking at two numbers, we want to try and work in the same way as we do mentally, which is left to right. But in this case, because we can't really mentally add up 64, 23, 39, 42, and because we're writing it down, working right to left is a better method. So the technique is to add downwards. So 4 add 3 add 9 add 2. And then to commute this, to put it in reverse order, we go up the column and start with 2, add 9, add 3, add 4. So let's have a go at this. 4 add 3 is 7, add 9 is 16, add 2 is 18. And if we were doing this just to speed things up, we wouldn't say it in that way. We would think in our head simply the answer. So we say 4, 7, 16, 18. Okay, now let's write that down. Obviously we can't write the 18, we put the 10 over here as a 1 in the tens column, and we hope that we've added that up correctly. The mental check is to go back up, so we go 2, 11, 14, 18, so we get the same answer, so we can be pretty confident, very confident in fact, that that was correct, and we can move on to the next column. So let's do that. 6 add 2 is 8, 11, 15, and before we write it down, we must go up the column again. 4, 7, 9, 15. So 15 was right. Add the 1, we get 16, or 168. So this is a technique that was used with people who were adding up columns of figures. So let's try it with some larger numbers, including decimals. 63.20, so we're working to two decimal places, and originally I guess this would have been £63.20. So let's have some more figures like that. So we've got, let's say, £17.49. Something, well, let's say £61.34, and I don't know, £58.27. Okay, so let's put our answer bar in and go from right to left going down first in the ones column. So 0, 9, 13, 20. But going back up, 7, 11, 20. So 20 was correct. Add, put our 2 into the tens column and go down the next column. So 2, 6, 9, 11, 2, 5, 9, 11. So 11 was correct. Add our 2, gives us 13, and carry over the 1. Okay. 3, 10, 11, 19. Check. 8, 9, 16, 19. Add our 1, 20. Bit faster. 6, 7, 13, 18. Check. 5, 11, 12, 18. So 18 was correct. Add our 2, we get 200. We end up with a total of £200 and 30 pence. And because we've included our double check, we can be pretty clear that even if we didn't use a calculator, we've definitely got the right amount of money. Now, that's good, but what if we had an accountant come in and check our figures, again without a calculator? What kind of technique would work for a double check that we've got something like this right? Well, this is something we call the digital root, and it's a very useful method for making sure that we've got something right. And if we got these kind of calculations in a test, for example, in the last 5 or 10 minutes of a test, going back and using the digital root method is a good way of just checking that we haven't made a mistake. Alright, let's have a look at how the digital root is calculated. 64 was our first number here. What we're doing with the digital root is we're adding the 2 digits together. So it's a rather strange operation. We are going to use an arrow because if we wrote that 64 is equal to 6 add 4, well, that wouldn't be correct. So we mustn't use an equal sign. But the digital root of 64 is 6 add 4, which is 10. And so now we have 2 digits, and we're going to simplify those to get down to 1 digit. So the aim with the digital root method is getting down to a single whole number digit, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So 10 becomes 1 add 0, and 1 add 0 is simply 1. So the digital root of 64 is 1. Let's do it with the other numbers so you can see how this works. 23, the digital root of 23 is 2 plus 3 equals 5. And in this case, we can go straight across and put the 5 over here because there's only 1 digit, so we've completed the job. 39 becomes 3 add 9, which is 12, which becomes 1 add 2, gives us 3. So the digital root of 39 is 3. Finally, we had 42, so the digital root of 42 is 4 add 2, gives us 6, and so 6 is our final answer. The digital root of 42 is 6. Now, this is useful to know because we're going to do something in a moment based on this idea, that the digital root of any answer, let's not write that, that looks like doctor, So we just erase that capital D. Let's write digital root as just simply dr. Okay, so the digital root of any answer, in this case 168, should be the same as all the other digital roots added together. In other words, the digital root of 64, the digital root of, what did we have, 23, the digital root of 39, and the digital root of 42. So this is an equation. The answer should add up to the sum on the other side of the equation. Well, let's see if it does. The digital root of 168, we're going to go vertically now because of the way that we've laid this out. So the digital root of 168 is 1, add 6, add 8. So that's 7 add 8, which is 15. Okay. Now we've got to do the second order of operations. So we've got 1 add 5, and we end up with 6. So the digital root of 168 is 6. And after a bit of practice, you can see that visually, you can do it mentally, although it's a good idea to write these things down so that you don't make any mistakes. So does it work on the other side of the equation? Do we end up with 6 as well? Well, the digital root of 64 we've already worked out is 1, so we'll write that down here. The digital root of 23 is 5. The digital root of 39 we said was 3, and the digital root of 42 is 6. Add these together and we should get another digital root. So 1 add 5 is 6, add 3 is 9, add 6 is 15. 15. But we're not finished. We've got 2 digits, we only want 1, so we go down, add the 1 and the 5, and we end up with 6. The digital root then of all of these added together is 6, and that's exactly the same as we had here, and so we can say that the answer, 168, is definitely correct because we've added the digital roots of these 4 numbers and got the same as the digital root here. We can't say definitely. We could have made some mistakes and it all added up coincidentally to the same thing, but it is highly likely that if the digital roots added together give us the same figure, then the calculation we made was correct and we didn't make any mistakes. So the digital root is a really good check, and it's a shame that it's not taught more in schools, and it's something you can quite easily learn, very simple, and if you could use it fluently, very quickly, then it's a good way of checking your sums. Okay, in the second part of the tutorial we'll look at why this sort of thing works and a little bit more about addition. But hopefully that's been helpful. Please practice, obviously, some more sums. Try longer lists of numbers, so see how long you can make your list. It should still work, you should still be able to do it, only gets a little bit more difficult. And also obviously try things like the decimals and larger numbers to see whether you can sum those efficiently as well. Okay, what I'm going to do in the last part of this video is just explore very briefly the digital roots numbering system. There's a lot that we could say about this, but the important thing about what we're doing here is we're trying to understand how it works and so that we can use it with confidence. Alright, let's have a look at this clock then that I've drawn here, and we can see that it is a rather strange clock. It starts at 1, it goes through 2, 3, 4, 5, 6, 7, 8, finishes at 9 before starting again and going round and round. Now this is because I want to compare the digital root system to our conventional counting numbers. So with the digital root system what we have is a finite set of numbers. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. and so it stops at 9. Those are the only numbers that we're allowed in the digital root system. If we compare it to our natural numbers, so we symbolize that with this N symbol here. The natural numbers also start at 1 and they go up in the same sort of way using whole numbers only, but they go on forever. And that creates important differences between the numbers we're used to, the counting system that we use to count any number that we can think of, and the digital root system, which is much more restricted. Alright, so why is this important? Well, if we think of the number line, is used for the set of integers. That's even more advanced than the natural numbering system, and it goes off in this direction, so we say -3, -2, as well as in the opposite direction. So the number line system gives us our concrete image for numbers when we're using them in normal everyday usage. But here we need to think of a clock, because the digital root system is so limited, it goes round only to 9 and then starts again. And I'll show you what I mean by this by trying just this very simple example. So let's do a 3-figure number, 462. So 462, if we do the digital root of 462, we end up with, well, it's 10, add 2 gives us 12, and the 2 digits from the 12 give us 3. In other words, we couldn't stop at 12 because we don't have 12 on our number system, on our clock here. So we had to keep going, add the digits again until we got to 3. Let's have a look at another example, 388. And what's going on this time is we've got 11 add 8 gives us a 19. We've got more than we're going to step around this clock more than a whole way round. We're going to go round 9, and then we're going to go one more and end up at 1. So we add the digits again, and we get 1 add 9 is 10. So we've got our 0 here when we get to the top of the clock, and we have to keep going because there's no 10, so the 1 add the 0 is 1. In other words, what we have with a 9 is what we call an identity. It's the thing that doesn't change anything. A bit like in our conventional numbering system when we've got a 6 and a 7 and a 0, we say, well, that's exactly the same as 6 plus 7. So when we've got a 0, we just cancel it because we know adding a 0 or subtracting a 0 doesn't make any difference. It's the same here. If we've got a 9 in our numbering system, in our digital roots numbering system, we should put a DR there so that we're clear about that, then we can just cancel it out because the 9 simply takes us all the way around, and so it's equivalent to the 0. Alright, why is all of this interesting and important? Well, let's say we've got something like 567, and let's add something very simple to it, like 12. Now we can easily do that in our head, so we won't use an algorithm. So we've got 567, add 12 gives us 579. Well, now we do our digital roots check. So we say, well, 5 add 6 is 11, add 7 gives us 18, and 18 is 1, 8 gives us finally 9. So we missed out a step there so that we could see this as clearly as we would normally if we were doing this. Okay, now the 1 and the 2 gives us 3. So we've got a 9 and a 3. Our 5, 7, 9 we can do just as quickly. So our 5 and 7 is 12. Add 9 gives us a 21. 5 and 7 is a 12. Add 9 gives us, it does gives us a 21. So we've got 3. So 9 add 3 doesn't make 3, so it might seem as if these aren't exactly the same. But this is why I've drawn out this clock system. We've got to remember that when we've got a 9 in the digital root system, we just can cancel it, and we say, well, 3 and 3. So the 3 and the 3 are the same, so we can be confident that our 579 is correct. So this can be a bit confusing, and the reason why we need to understand it really carefully is because we wouldn't want to think that the digital root system was unreliable, and that if we get results here that add up to 12, and that's not the same as 3, we wouldn't want to think, oh, we must have done our calculations wrong, we better redo it. It could waste an awful lot of time. We could believe that this digital root system is unreliable. In fact, it's perfectly reliable as long as we remember this thing about the 9s. We also might get a 0 in here, and that would be the same as a 9. So 9s and 0s we simply cancel, and then we will get a reliable result. We will get a thing that we can use to check. So now let's try it with subtraction. Does it work with subtraction? Well, it should do, but let's see. So we've got 5, 6, 7, subtract 12 this time. And again, we can do it straightforwardly in our head. So we've got 555 as our result. 5 add 6 add 7 gives us a digital root of 11 add 7, 9 again. And the same here. We already know that our digital root of 12 is 3. So what happens down here? We've got 5 and 5 and 5, in other words 3 times 5. 15, that's 1 and 5, gives us 6. And immediately we can see, well, this is working nicely. The 3 from the 9, 9 take 3, gives us 6. Again, though, we can get into confusion if we're not careful. So I'm going to just add, well, let's see, add 2 to it to give us a slightly different result. So we're going to say 5, 6, 9 this time. Subtract 12 again will give us a result of 5, 5, 7. Now in this situation we're going to get something like this. So let's work it out. 5 add 6 is 11, add 9 gives us a digital root of 20. 1 add 2 gives us a digital root of 3. So at first sight this is rather strange because the digital root here will end up as 2, and 2 is smaller than 3. Let's look at the answer to see where we're trying to get to. 5 add 5 is 10. Add 7 is 17. 1 add 7 is 8. So we've got a 2 here, a 3 and an 8. At first sight it seems that there's no relationship between 2, 3 and 8, so we might be worried. And again, we must have a strong understanding of this clock system so that we don't panic and don't think that we've gone wrong here somewhere and start to correct it. What we've actually got here is a negative 1. We've got 2 take away 3, giving us negative 1 equals minus 1. Now negative 1 is simply going backwards here, so it is going to be the same as our 8. We can see that more clearly perhaps if whenever we've got a negative we simply add 9. So negative 1 add, let's do it down here, negative 1 becomes add 9 becomes 8, and so now we've got the 8 being the same top and bottom. So this is a system that does work in addition, subtraction, and you also might go on to try and use it in multiplication and division. It's a very interesting system, but what we've said is we need to understand how it works in order not to get worried about it and to think that it's unreliable and that needs to come with a health warning.